So, here is the quick recap of the last class. Electric dipole, as we discussed yesterday, that dipole is made up of two charged particles of equal magnitude but opposite sign. So, one positive charged particle and another negative charged particle. This system is called electric dipole, right. So, for electric dipole we defined physical parameter called dipole moment, right. So, one positive charged particle and another negative charged particle kept at a certain distance, system is called electric dipole, right. So, for this one we defined physical parameter called dipole moment, and the dipole moment is defined as charge on one of the particle into separation. So, Q into D, D is the separation between them. As the dipole moment is a vector quantity, by convention we define direction from negative charge to positive charge, right. So, from negative charge towards positive charge, this will be the direction of dipole moment. So, we discuss few numerical based on dipole moment. We calculated dipole moment for different situation. Now, let us start. So, if I want to find out the field around the dipole, electric field around the dipole, one is positive charge particle, another is negative charge particle, and both have the equal magnitude. So, what all lines originating from positive charge will terminate at negative charge, and in space the field lines will be something like this. See, so look at this animation, lines are originating from positive charge and terminating at negative charge, right. You can see at any point on the bisector, field line is towards negative x direction, right. And the dipole moment, as this is negative charge particle and this is positive charge particle, this is negative charge particle and this one is positive charge particle. Let us see once again. So, negative charge particle, positive charge particle, lines are originating from positive charge and terminating at negative charge. You can see field lines here at the bisector, they are always along negative x direction, and if you look at any point on the axis outside the dipole, somewhere here the field line will be something like this along positive direction of x axis. Similarly, these lines will take turn and finally they will terminate at negative charge. Somewhere here field will have this direction. So, outside dipole field lines outside the dipole on the axis of dipole, field lines are along the positive x direction, while on bisector it will be opposite to x axis, right. So, here the dipole moment will be from negative to positive, it will be like this dipole moment. So, you can see, let us play it once again. So, you can see that along the direction of dipole moment you will be having electric field on the axis of dipole, while on the line which is bisecting these two, line joining these two, it will be opposite to the dipole moment. So, electric field here in this direction, dipole moment in this direction, right. So, I hope you got clarity how field will be in space due to this combination, positive and negative combination, how would be the field in space. Now, I want to find out the value of the field at any general point. If I ask what is the field direction and magnitude at that particular point. So, at this particular point, this positive charge will produce field along the line joining away, and this negative charge will produce field along the line joining towards, right. So, this is the field produced by positive charge and this is the field produced by this negative charge. So the resultant will give you the direction of net field at that particular point, right. So vectorially if I add these two, then using parallelogram, then field here will be something like this, net field. On axis, outside dipole, it is along the dipole moment. Perpendicular to that, look at this particular point. So this positive charge will produce field in this direction away, and this negative charge will produce field towards, right. So resultant of these two will be in this direction. That is why we got the field line at this particular point in this direction. If you draw tangent, then you will get this direction. So this is the direction of net field. Which is coming opposite to the dipole moment. So we are interested in finding the field at any general point in a space due to electric dipole. So let us see how to find out. So first we will see what would be the field on the axis of dipole, right. Instead of taking dipole, if I take say water molecule, so water molecule here there will be slightly positive charge on hydrogen, and on oxygen there will be slightly negative charge because electron affinity of oxygen is more as compared to hydrogen. Similarly here these electron will get shifted towards oxygen slightly, it will have slightly negative charge because of this shifting also. So this is forming one dipole and this is forming another dipole, right. Direction is from negative to positive like this, and here direction is from negative to positive like this. So resultant of these two will give you the net dipole moment due to this molecule. But the field line in a space, if I draw field line in a space in 3 dimension, look at this animation. So these two are representing hydrogen molecules, these two molecules, and this is oxygen molecule. You can see lines are originating from oxygen molecule and hydrogen molecule and terminating at oxygen molecule. So in a space field lines will be like this. Let us see once again. So it will be little more complicated because there is a combination of 3 charges, right, 2 negative 1 positive. So field will be little more complicated, but this would be the field pattern in space due to water molecule. Now here we are interested in dipoles only. So we will talk about the dipole. As I said earlier, because of the dipole I want to find out field at this particular point. Let this be a negative charge, so this is minus q and this is plus q. And I want to find out field at distance r from center of dipole. So this is r, this distance from center, this distance is r. And the gap between these two charges is 2L. So generally the gap between these two charges will be very small as compared to this r, but just to make you understand I am drawing this big diagram, right. So at any point outside dipole, especially on the axis, this negative charge will produce field in this direction, and this positive charge will produce field in this direction. As this positive charge is near to this point, it will produce more field as compared to the field produced by this negative charge, right. So, both are producing field in opposite direction. If I want to find out resultant of these two fields, what I can write, net field at that particular point is equal to so net field at that particular point is field produced by positive charge minus field produced by negative charge. Both are in opposite direction. I will subtract their magnitude. So, I am writing magnitudes here and subtracting. Field produced by positive charge. What is the separation? From here to here, if distance is r and this total distance is 2l, then half of that distance will be l, this distance will be l. So, from positive charge, this distance will be r minus l. So, this separation is coming r minus l minus r minus l, and from this charge, if this is l and this distance is r, this distance is l plus r, and due to point charge, field at distance r, formula is kq by r square, kq by r square. So, because of this positive charge at this particular point, I will write kq divided by separation square r minus l whole square minus field produced by this negative charge is at distance r plus l from the point where we want to find out field, P point where we want to find out field. So, k q divided by r plus l whole square, right. If I simplify this one, then I will get k q, multiply this one to this one, this will become r square minus l square whole square, and then when you multiply this here and this here, this r square l square will get cancelled out, 2rl will be left here and 2rl will be left here, with minus sign it will become positive, and 2rl plus 2rl will make it 4rl. So, here it will become 4rl. Now, this k, look at this one, look at this part. If I ask what is the dipole moment of this arrangement, dipole moment is charge into separation, separation is 2l. So, dipole moment of this arrangement is charge into separation 2l. Here 4 is written, q into 4 into l. So, that means that can be written as 2 into dipole moment. So, that can be written 2 into dipole moment. This term I am writing 2 into dipole moment. Then this r small r divided by r square minus l square whole square, r square minus l square whole square. Now, look at the expression. If I say this L, this separation is very small as compared to the point where we want to find out the field. So, R is much larger if R is very large as compared to L, then whole expression can be converted into K. This will become, as this is very small as compared to R, this will become 0 as compared to R, 0, then this will be R to the power 4, and this R and R to the power 4 will get cancelled out. You will get 2p divided by R cube. So, electric field at any point on the axis of dipole is written by this. Instead of taking point somewhere here, if I take point somewhere here, look at this one. So, this negative will create larger field at this particular point as compared to the field created by this positive charge in opposite direction. So, as this one is greater than this one, the resultant will come in this direction only. So, whatever be the direction of dipole moment from negative to positive, same will be the direction of electric field outside the dipole. So, I can also write this one in vector form. So, E vector is equal to 2k P vector divided by R cube, right. So, this is the field at axis of the dipole outside the dipole. So, I hope this derivation is clear. Very important expression we will be frequently using. So, do remember this expression 2kp vector R cube on the axis of dipole, and the direction remains same, whatever direction of dipole moment, same with the direction of electric field, right. So, very simple procedure. Two charges, at this point I want to find out net field, as they are creating field in opposite direction, I will subtract and simplify, then take approximation, I will get this. I hope derivation is clear. Now, this is for the point on the axis of dipole. If I take bisector, so two charges negative and positive, and I take bisector, and on bisector I want to find out field. Let us see. So, in animation you have seen that the direction of field will be like this at this particular point. Right. Let us calculate that value. So, here we got minus q charge and this one is plus q, and we want to find out net field at that particular point. So, due to this negative charge, field will be towards the charge. At this particular point we want to find out field, line joining, and the direction of field will be something like this, field produced by negative charge. This positive charge will produce field along the line joining away. Now, as the magnitude of charge same and the separation between point and charge is same, this E plus will have same magnitude as that of E minus. So, magnitude wise E plus same as E minus. let's call it some E, right. So both are same, let's call it some E naught or E, because net field we will be writing with E, so let's call it E naught. If this angle is theta, the angle made here, this angle will be theta, as this angle is theta, this angle will be theta, and this angle will also be theta, right. So you can see that E plus cos theta and E minus cos theta, they will get added, and E plus sin theta and this E minus sin theta, they will get cancelled out. So if I separately draw diagram, this plus will have two components, one in this direction and another in this direction. Similarly, this E minus will have two components, E minus cos theta and E minus sin theta. As E plus and E minus, they have got the same magnitude, these two will cancel each other. That means I need to add these two. As I am writing E plus and E minus both as E naught, that means net field coming at that particular point, net field coming at that particular point will be E plus cos theta, E minus cos theta, and that I am writing E naught. So this will become 2 E naught cos theta. So the resultant of these two, if I use parallelogram, the resultant of these two is coming in this direction. That I am calling E net. So I hope this part is clear. We just resolve the component, x component got added and y component got cancelled out. So now I can remove this one. Let's substitute the value. So net field is 2 E naught, field created by any one of these two at this particular point. So this from here to here, total distance is 2L, this distance will be L, and I am interested in finding field at distance r from the center of the dipole. So this distance will be under root r square plus L square, right. Formula is kq by r square. So k q divided by separation square, this separation whole square. So under root whole square will give you r square plus L square, right. This separation whole square, you will get this. Now cos theta, cos theta is base upon hypotenuse, base is L, hypotenuse is this. So L divided by under root r square plus L square. Now I need to simplify this one. Look at this part, 2 Q L, that is nothing but dipole moment. 2q charge into 2L is dipole moment, right. So, this I can write dipole moment. So, this will become two will go, it will make it dipole moment. So, you will get K, this will be dipole moment P divided by R square plus L square to the power 3 by 2. Now, again using condition, if this distance is quite large as compared to this separation, if R is quite large as compared to L, the whole expression can be written, this L is very small as compared to R. So, here I can neglect L with respect to R, this will become R square to the power 3 by 2. So, 2 and 2 will get cancelled out, you will get cube. So, K dipole moment divided by R cube will be the magnitude of net field at that particular point. If I want to write in vector form, you can see that the direction of dipole moment from negative to positive and the direction of field, they are in opposite direction. So, this P vector and this E vector, they are in opposite direction, right. So, this can be written E is equal to minus k P vector, both are in opposite direction, divided by R cube. So, for any point on the axis at distance r, it is 2 times as that of at the same distance on the bisector, right. So, magnitude of field at any point on the axis is 2 times as compared to what we are getting on the axis, only magnitude wise. Direction you can find out from the expression, right. So, previous case when we were calculating on the axis at distance r, we got on the axis at distance r, we got 2 times 2p divided by r cube. Here we are getting p divided by r cube. Previous case they were in same direction, dipole moment and field, they were in same direction. In this case dipole moment and field both are in opposite direction. So, you have to keep these 2 points in mind to find the field at any general point. So, now let us find out the field at general point. For example, if I want to find out field somewhere here, so I can use previous result and this result to derive the expression for general point, right. Let us see. So, at any general point, so this is the dipole, instead of representing dipole this way, I can also represent dipole this way, where arrow represents the direction of dipole moment. So, this is nothing but dipole, where here we have negative charge and here we have positive charge, right. So, this is one of the way of expressing the field. Now, see, at this particular point, if you are interested in calculating the dipole moment, calculating the field, what I can do, I can resolve, because dipole moment is a vector quantity, I can resolve this dipole in 2 directions, one along the line, one along the line and another perpendicular to that. So, in two mutually perpendicular direction I can resolve the component. The one which is coming along the line joining, that will be, if the dipole moment of this one is P, the component of this dipole moment along the line joining will be P cos theta. So, if I resolve, I will get this as P cos theta and this as P sin theta. If this is the vector and I want to resolve the vector in two mutually perpendicular direction and this angle is theta. So, this component along the angle cos theta, you can easily remember, along the angle cos theta and perpendicular to that. So, perpendicular to this will be in this direction, this component will be P sin theta. So, what I will do? I will resolve this P in two direction, P cos theta and P sin theta, right. Because of this P cos theta, this point will be the point on the axis, and because of this P sin theta, this point will be, you can see here, just look at P cos theta only. So, if I just hide this part, because of this one, this point is the point on the axis of the dipole. So, this point for this dipole, this is the point on the axis, while if I hide this one, because of this P sin theta, this is the point on the bisector, and we know because of dipole on the axis, field is along the direction of dipole moment. So, this will create field in this direction, while for bisector the direction of field is opposite to the direction of dipole moment. So, here we have got dipole moment in this direction and the field will be opposite to the dipole moment this way. So, this dipole can be resolved into two components, one along the line and another perpendicular to the line, and we will see the contribution of both the dipole at this particular point, and then we will add the contribution. So, I hope approach is clear, how to approach to find the net field at that particular point. Now, let us get back to the original diagram. So, because of this P cos theta, I am getting field here in this direction, right. So, this is the field created by P cos theta, I write electric field created by P cos theta. Now, it is another component for this P cos theta, this is the point on the axis to same direction. Now, because of P sin theta, so this component is representing P sin theta. So, due to this P sin theta, field here will be opposite to the dipole moment, because this is the point on the bisector of this dipole. So, this point is the bisector of dipole, and we have just seen that the field will be in opposite direction. So, because of this P sin theta, here field will be in this direction, right. So, this is the field because of P sin theta. If I add them vectorially, then I will get the net field at this particular point. So, let us add them vectorially. I will again write it here. This is E because of P cos theta. I hope now this diagram is clear. So now what I need to do, I need to add them vectorially. This angle will be 90 degree, right. So it will be something like this. If I draw parallelogram, this will be the parallelogram. I need to add them vectorially. So the resultant will be something like this. This is net field. So what I can write, first let's find out what is the field produced by P cos theta at that particular point. So field produced by P cos theta, that will be equal to axial point. Axial point we have seen 2k P divided by r cube, where instead of P now we need to write P cos theta component. Axial point 2 times just now we have derived. This one on bisector, so contribution of this one Kp sin theta divided by r cube. As this is the bisector point, we have seen that field at axis at distance r is 2 times as that of what is produced at the bisector. Now as these two are making 90 degree, I can square and add them. So if I want net field, so what I can write is E P cos theta whole square plus E P sin theta whole square. You can see here you will get 4 cos square, and here you will get sin square. Sin square and 1 cos square will give you 1, sin square theta plus cos square theta will be 1, and then instead of 4 cos square, now there will be 3 cos square left inside. These common term we can take out, kpr cube we can take out. So outside you will get kpr cube and inside you will get under root 3 cos square theta plus 1. So substitute this value here and this value here and simplify, then you will get kpr cube, that is common, that I have taken out, inside under root 1 plus 3 cos square theta, right. Now as this is a vector quantity, field is a vector quantity, we have to tell about the direction. So if I assume this angle to be phi, so the angle made by field with line joining center to the point, with that field is making phi angle, was the relation between tan phi and theta. Now you can see that I can write tan phi is equal to tan phi perpendicular is what? EP sin theta. So field produced by P sin theta divided by field produced by cos theta. So that means if you divide sin theta by cos theta, then kpr cube will get cancelled out. Numerator you will get sin theta and denominator you will get by 2 cos theta. So this will come sin theta divided by 2 cos theta. So sin theta divided by cos theta can be written tan theta, So this will become tan theta by 2. So if I simplify, then I will get tan phi is equal to tan theta by 2. So now I have magnitude and I have direction, right. So when you were on x-axis field was in this direction, and from here maintaining same distance, if you go like this, when you reach to the bisector, field will be in opposite direction, right. So from this direction field will turn and then it will become like this. Maintaining distance r, if you go from this point which is on the axis to the bisector, you can see for this point field was in this direction, right. And when you reach to the bisector, maintaining the same distance, you got field in this direction, right. This is the direction of field, and as we go here, field will be in this direction. That means at different point the direction of field will be different. At this particular point it is in this direction, somewhere here it will be in this direction, somewhere here it will be in this direction, somewhere here it will be in this direction, then it will be in this direction, somewhere here it will be in this direction, and when you reach to exactly bisector it will be like this. So when you are rotating this r vector by 90 degree, you can see that field gets rotated by 180 degree. Field is getting rotated by 180 degree from being along positive x direction to negative x direction. This vector got rotated by 180 degree. So I hope these two expressions are clear. This is the expression for net magnetic field at any point around dipole, and this is the direction of field at that particular point. Now, I hope this point is also clear. Let us see one simple example based on this concept. If the dipole is placed on x-axis, find the angle theta for which electric field produced by dipole is parallel to y-axis. So I am keeping dipole this way, and I want to find out the angle theta for which the field at this particular point is along y-axis. I want net field in this direction, right. So what should be this angle for this to happen? Dipole is placed on x-axis, but the field is parallel to y-axis. At what angle this will happen? That I need to find out, right. We know that the angle made by field with the line joining phi, that is given by tan phi is equal to tan theta by 2, right. Tan phi is equal to tan theta by 2, and you know that if this is along x-axis and this is along y-axis, then phi will be 90 minus theta, or I can say if this is along y axis and this is along x axis, this total angle phi plus theta has to be 90 degree. So from here if I substitute the value of phi, from this condition if I substitute the value of phi, then I will get 10 90 minus theta is equal to 10 theta, and this I can write cot theta, 10 90 minus theta cot theta. This can be written 1 by 10 theta. That means we are getting 10 theta is equal to, this will become 10 square theta. That means we are getting theta is equal to 10 inverse root 2. We are getting theta is equal to 10 inverse root 2. So for this particular angle, for this particular theta, the field at this particular point will be along y axis, right. So any point at any distance you take, whether you take distance this r dash or r double dash, everywhere field lines will be, or net field will be along y axis, parallel to y axis. But condition is this separation must be quite large as compared to this separation. So we use the result after approximation. So final outcome will be valid only when approximation is valid. So separation between positive and negative charge must be very small as compared to this separation, then only this result is valid, right. Now we have just seen the expression of field, now we will see the expression of potential. I want to find out potential at this particular point. So obviously here there will be negative charge and here there will be positive charge. And due to this dipole, I want to find out potential at this particular point. Field we have just seen. Dealing potential is little easy as compared to dealing field, because field is a vector quantity, vectorially we have to add. Potential as being scalar, you can directly add the potential developed by minus q charge and plus q charge at that particular point. So this minus q charge, how much potential it creates here, you add that to whatever potential is created by this plus q charge, right. So if I assume this distance this as r minus, right, from negative charge r minus, and this distance, this I call r plus, and this r is distance from the center of dipole. So this r is this distance, right, do not get confused. This r is this distance, right. So let us first write the expression for potential. So potential at that particular point is potential due to negative charge, potential due to minus q charge plus potential due to plus q charge. So potential due to minus q charge, potential is scalar quantity, charge must be kept with sign. So formula is kq by r. So here I write k minus q divided by r minus plus because this separation is R minus KQ by R with sign. Due to positive charge, K plus Q divided by R plus, if I simplify this one, then I will get, see, KQ I can take out, this minus will go here and plus will come this side, right, R plus will come this side. So, this can be written R minus minus R plus divided by R minus into R plus. Now, we need to simplify the expression. So, R minus minus R plus, the difference between this distance and this distance, to find the difference, because this R is very large, this R is very large. So, as this R is very large, to find the difference, what I can do, I can draw perpendicular. So, I have drawn perpendicular. From here onwards, this distance will be same as this distance will be same as this distance. So, the difference R minus R plus is only because of this. Let us see once again. From here this is R minus, from here this is R plus. I need the value of R minus minus R plus. That means I require the difference between this distance and this distance. To find out the difference, what I am doing, I am drawing perpendicular over R minus. What I am saying, from here onwards, because this distance is very large, from here onwards this distance will be equal to this distance. That means difference is only because of this. So, this is nothing but R minus minus R plus. This is nothing but R minus minus R plus. And look at this triangle, right. Visualize the situation once again. Two charges are kept at very small distance, right, and I have taken the point P somewhere here. So, diagram is something like this. Just to make you understand, I am drawing this big diagram, right. Now, if I join this one to the center of dipole, I join this point to this one and I join this point to this one, the angle made by this and this will almost be equal. So, this will be, if I am considering this as theta, this will be approximately theta and this will be theta. Two points are very close and at far away point we need to find out. So, whatever be the angle made by line joining center to the point, same will be the angle made by line joining the point N negative charge as well as the point N positive charge. So, these angle will be almost equal because this gap is very small. So, I can consider this angle to be almost theta. If this gap is, you assume 2L, if this gap is 2L, this is base, this is perpendicular and this is hypotenuse. This is base along the angle, this is base, this is perpendicular and this is hypotenuse. So, if I ask what is the gap, then you need to resolve 2L in this direction, that is nothing but 2L cos theta. So, this gap is coming 2L cos theta. Now, I require the value of R minus into R plus, R minus into R plus. That can be approximately written because see, look at this diagram. This is R minus, this is R plus and this is R. R minus R plus and this is R. So I can write R plus is almost same as R minus, which is almost same as R. They all are approximately same. If they all are approximately same, R minus into R plus can be approximately written R square. So I hope these two are clear. From diagram and approximation we got these two value, and now we can substitute it here. So this is a symbol of approximately equal, right? So this concept is clear. I will erase this. So here I can write 2L cos theta, and here I can write R square. So if you simplify, you can see you will get Kp cos theta R square by V is equal to K Q into 2L cos theta divided by R square we are getting, right? And this I can write in terms of dipole moment. Charge into separation will give you dipole moment. So charge into separation, this is nothing but dipole moment. So it can be written P, right, cos theta R square. Now dipole is a vector quantity. You are writing this P in magnitude. So everything written here is in magnitude form. Every vector which is written here, that is in vector is magnitude form, right? So I hope this derivation is clear. Now, so I'll first clear the derivation to understand one point. Potential is scalar quantity. So because of negative we calculated, positive we calculated, we added them. After adding, we simplify. After simplification, we got these two requirements. These two requirements from diagram, we got 2L cos theta and R square. So substituting 2L cos theta here and R square here, I will get this one, right? Now, let's first analyze what we have got. Look at this diagram. This is dipole. If I draw circle of radius r, if I draw circle of radius r, right? So I kept dipole at origin. This is x axis, this is y axis, and this is circle of radius r. If I analyze all critical points, look at this point. The field coming at this point will be along the dipole moment, and the value of field I am asking, value of field is 2 k p divided by r cube. That is the value of field. And what is the value of potential at this point? Potential at this point, if you substitute for this point, you need to substitute theta is equal to 0. So if you substitute theta is equal to 0, you will get kp divided by r square. So here you will get kp divided by r square. Now when you are at this particular point, we have seen that field is opposite to the dipole moment. The value of field here is kp divided by r cube, and the value of potential at this point is 0, because when you substitute theta is equal to 90 degree, this quantity will become 0, and obviously it has to be, because from here this separation is same as this separation. One is negative charge, it will produce negative potential here, and positive charge will produce same amount of positive potential, and they will get cancelled out, and you will get 0 potential at that particular point, right. So potential here is 0. Same logic I can extend for this point. Here potential will be 0, potential here is 0, and the field will be opposite to the dipole moment, so field will be like this. So the value of field is, value of this field is E we are getting at this particular point, again what we are getting there, right. So k p divided by r cube. If you remember the expression we got for field, that was k p divided by r cube in bracket 3 cos square theta plus 1. So whether you substitute theta is equal to 90 degree or theta is equal to 270 degree, in both the cases this quantity will be 0, cos 90 0, right. So whether you substitute theta 90 or theta, whether you substitute theta pi by 2 or 3 pi by 2, in both the cases this value will be 0. If this value is 0, then this will become kp upon r cube only. So here and here the direction of field will be opposite and magnitude same, potential 0 0. Now look at this point, the direction of field will be still same as that of dipole moment, because if I substitute theta is equal to, for this particular point, if I substitute theta is equal to 180 degree, cos 180 degree minus 1 whole square, that will be plus 1. So this will become 3 plus 1 4, under root 4 2. So here you will get field E is equal to 2k p divided by r cube, and the potential at this particular point, look at the expression of potential we just got, kp cos theta divided by r square. If I substitute cos theta, theta is equal to 180 degree, if I substitute 180 degree here, then I will get minus 1. That means here here potential is coming the least one. So on this circle on this circle if I talk about, this will be the point of maximum potential. Here potential will be maximum. So, this is the maximum potential V max, and this is the point of minimum potential V min. This is the point for maximum field and this will be the point of minimum field. So, here field will be minimum, because if you look at this expression of field, when theta is 90 degree, at that situation only this function will assume the least value. So, for theta is equal to 90 degree or pi by 2 or 3 pi by 2, for this point and this point, this function will achieve the least value. So, here this will be the point of minimum field. So, this is the point of maximum potential, these are the point of zero potential, and this is the point of least potential, scalar quantity with negative sign we are getting. This is the point of maximum field, because highest value when this whole expression will become 1, cos square will become 1, cos square will become 1, then this whole function will assume its maximum value, right. So, at this point field is maximum, potential is maximum, while for this particular point potential is minimum but field is maximum. This point and this point field is minimum but potential is 0. So, this is a complete analysis of field and potential due to dipole, right. I hope you understood each and every point. So, you have to remember these two formula, that field is Kp divided by r cube under root 3 cos square theta plus 1 and V is equal to Kp cos theta divided by r cube. So, we will be using these expressions. Now, let us see next concept. So, what if I place the dipole in uniform field? So, we have seen the field created by dipole, potential created by dipole, but what if I place that dipole inside external field? So, field already exists in space and I took one dipole and place it in space. How much net force it will experience and what would be the torque experienced by the dipole? If I place dipole in uniform field, like the one given in the situation, right. So, field is uniform. So, this is the example of uniform field, right, and field is there everywhere. So, if I place dipole this way or any way, the force experienced by this positive charge will be along the field, that will be Q into E, and force experienced by this negative charge will be opposite to the field. So, if I draw free body diagram of the dipole, QE force acts in this direction and same amount of force is acting. Actually, we have already considered the direction. If I am writing with the direction opposite to the field, force will be acting, right. So, magnitude wise this force and this force will be same, but direction opposite, they will cancel each other. So, net force experienced by dipole will be 0, right. So, if I write net force, net, so this is experiencing QE in negative x direction and this is experiencing QE in positive x direction. So, magnitude wise if I want to write, I will write QE and with vector QE I cap for this one and plus QE I cap, because this is in negative x direction, minus I cap, these two will cancel each other and you are getting net force experienced by dipole is 0. So, no matter how you place the dipole in the field, the net force it experiences is 0. If you place dipole this way, Negative charge, positive charge, right? So positive charge will experience force along the field, that will be QE this way, and negative charge will experience force opposite to the field, that is QE this way, right? If I draw free body diagram of dipole, then these two will cancel each other and the net force is 0, right? So no matter how we place the dipole in the field, the net force it experiences is 0. If we are interested in finding the torque, torque may or may not be 0 depending on the situation. At this particular moment, both the forces are passing through center. This is not providing any torque about center, this force is not providing any torque about center. Similarly, this force is also not providing torque about center. Formula for torque is R cross F. That means R vector mod F vector mod sin theta. So R vector, you can see this is R vector and this is force vector, both are in same direction. R vector and force vector both are in same direction, the angle will be 0. If angle is 0, torque will be 0. So the torque produced by this force and this force both are 0. So net torque on dipole at this moment 0, net force on dipole at this moment is 0. Net force on dipole at this moment is 0, but net torque on dipole at this moment is non-zero. So torque may or may not be 0, but force will always be 0, right? On what factor torque will depend? Let's figure out. So we understood first point, that no matter how we are placing it, net force is always 0. So this is the first point. Now let's see next point. So force I discuss, force we have discussed. Now we are talking about torque. Torque formula R cross F. If body is in equilibrium about any point, you can find out torque, right? So if I take this point, because body is in translational equilibrium, we have first proved. So any point you can take, about any point torque will come same. So you take this point, this point, this point, anywhere you will get the same value of torque, right? So I have taken the center. So you can see that about center, this force is trying to rotate the dipole in clockwise. R cross F formula is R cross F, R vector cross F vector. So with respect to this point, this is the position vector and this is R vector. So rotate, right hand rule, rotate R towards F. So R cross F, torque is coming inward and the sense is clockwise, right? So I am taking clockwise sense positive, right? Clockwise sense positive. Now for this one, R cross F, for this one you can see that R in this direction, this is R vector, this is R vector and this is F vector. So rotate R towards F, again torque is coming inward direction and sense is clockwise. So both are providing torque in the same sense. So I can write torque because of positive and because of negative. Because of positive if this total distance is 2L, if I assume this total distance from here to here 2L, then perpendicular distance, I can write force, this can also be written as R perpendicular into F, right. So, if you extend the force and draw perpendicular, this is L, and if I extend this one, extend the force and draw perpendicular, then this distance will be same as this distance. If this is L, this angle is theta, this perpendicular distance will be L sin theta. So, I can write force into perpendicular distance, that is QE into L sin theta, plus, because of the negative charge, force and draw perpendicular, right, extend the force and draw perpendicular. So, if this angle is theta, this angle will be theta, this is L, this perpendicular distance will be L sin theta. So, again the same thing will come. So, I can write QE into L sin theta. If I simplify this one, then I will get 2QLE sin theta. Charge into separation, separation is 2L and charge is Q. Charge into separation, this will give dipole moment P, PE sin theta. This is the magnitude of torque, right? And if I am interested in writing torque in vector form, so let us write torque in vector form. So, this can be written tau is equal to P vector cross E vector. Let us check the direction once. We will check the direction by this one, right. So, dipole moment from negative to positive in this direction, and field is in this direction, field is along x-axis. Now, we need to do cross product, right hand rule. So, rotate first vector towards second vector. So, rotate P towards E, we are getting thumb in inward direction, that means torque is coming in the same direction what we have got here. So, torque can also be written as P vector cross E vector. This is the torque experienced by dipole in uniform field. What happens when dipole is kept in non-uniform field? What is the work performed? What is the potential energy associated? That all we will see in next class. So, I hope you have enjoyed today's class, right. I have given you assignment based on the dipole, download the assignment and solve it. So, thanks for watching.